I now call to order the Society's 2,446th meeting in what is now the 151st year since its founding on March 13, 1871. Good evening, everyone. Good evening. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium, and everyone tuning in on Zoom and on YouTube, to tonight's lecture by Mark Clampin. The Society is grateful to the sponsors of the 2022-2023 lecture series for their support. The Policy Studies Organization, in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. I am pleased to announce the following new members: Richard James, Emeritus Professor of Earth Sciences and Geology, interested in Earth Sciences, Astronomy, and Geology of Planetary Bodies, who learned of PSW from a reference on the Carnegie Institution website. A.J. Kathari, President of Astrox Corporation, interested in hypersonics, rockets, space exploration, and nuclear propulsion, who learned of PSW from PSW member Adarsh Deepak. Bilal Sliman, CIO of Trim Illusion, interested in mathematics, algorithms, astrophysics, and socioeconomics, who learned of PSW through the Cosmos Club. Tonight's speaker, Mark Clampin, previously spoke on PSW's Hubble 25th anniversary panel, and his interests will be clear in part from tonight's lecture. We welcome them all to membership. Very good, yes, welcome. If you're not a member and you would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the home page. It's very easy. We welcome new members and we appreciate donations. Janice Soreth will now read the minutes of the 2,464th meeting and the lecture by Andy Rivkin and Andy Chang on DART, NASA's Double Asteroid Redirection Mission, prepared by Recording Secretary James Webb. Janice, the stage is yours.
Thank you, Larry. Good evening. On October 7, 2022, from the Powell Auditorium of the Cosmos Club in Washington, D.C., streaming online via Zoom and the PSW Science YouTube channel, President Larry Milstein called the 2,464th meeting of the Society to order at 8:04 p.m. Eastern Daylight Time. He announced the order of business and welcomed new members. The recording secretary read the minutes of the previous meeting. President Milstein then introduced the two speakers for the evening, Andrew Cheng and Andrew Rivkin, both from the Johns Hopkins Applied Physics Laboratory. Cheng is co-lead investigator for the Double Asteroid Redirection Test, aka DART, and Rivkin is the investigational lead. Their joint lecture was titled DART, the Double Asteroid Redirection Test, Protecting Earth from Planetary Impacts. Rivkin began the presentation showing animations of what the DART team expected to happen if the test was successful. He then explained the purpose of the mission. Between 100 and 300 tons of material impacts the Earth daily. While most material is millimeter-sized or smaller, occasionally larger objects strike our planet's surface. The speaker then used videos and photographs to describe notable recent and historic impacts, including the 1992 Peekskill impact, the 2013 Chelyabinsk impact, and the prehistoric Barringer impact. Scientists believe objects approximately 1,000 meters or so across are big enough to collapse civilization and will strike every 500,000 years on average. Because impacts have been recorded around the world, they present a uniquely global threat. In 2018, the United States developed the National Near-Earth Object Preparedness Strategy and Action Plan. One of the plan's goals is to mitigate an identified asteroid threat. For asteroids roughly 100 meters across, the plan calls for kinetic impactors to divert the object's path. Rifkin said that is where DART plays a role. Rifkin said the lowest cost way to observably test changing asteroid speeds by centimeters per second is to look at asteroid satellites. For that reason, the DART team identified the binary asteroid Didymos system and chose asteroid satellite Dimorphos as its target. Didymos is 780 meters across, while Dimorphos is 160 meters across. Their centers are 1,180 meters apart. Andrew Chang then took to the podium to discuss DART's mission and early results. DART launched on November 24th, 2021, carrying Lycia Cube, an Italian space agency CubeSat for imaging the mission, and struck Dimorphos on September 26, 2022. DART's impact is confirmed, and the team is now evaluating its success in achieving its remaining 3 mission requirements: causing a 73-second or greater change in the Dimorphos orbital period, measuring the mirroring change to within 7.3 seconds from ground-based observations, and measuring beta and characterizing the impact site and dynamics. Beta is the momentum transfer to the asteroid. Chang said the beta could be measured based on the amount of expelled ejecta from the surface. To properly correlate ejecta with momentum, the DART team needs to first understand the impact angle and the asteroid's physical properties. Chang then showed multiple simulated impact models assuming different asteroid material properties. The weaker the material, the greater the ejecta, and the larger the crater. Chang then described DART's key technologies, including an autonomous navigation system, Draco imager, Next-C ion propulsion engine, rollout solar arrays, CoreSat avionics, radial slot array, transformational solar array concentrators, and the Italian CubeSat Lycia Cube. As Chang referenced these instruments for the remainder of his talk, he showed images and described their functions in greater detail. DART first detected Dimorphos approximately 45 days before impact and released Lycia Cube around 15 days out. SmartNav took over steering 8 hours from impact, and 4 hours out, the spacecraft was fully autonomous. Chang then used simulated images to illustrate in detail DART's minute-by-minute progress toward impact. SmartNav ceased maneuvering the craft approximately 500 miles out, and DART finished its journey on a glide path to impact. Chang then narrated in detail a movie compiled from Draco images of DART's final minutes up to the second before impact. He concluded by showing and describing Lycia Cube images of the impact plume. He said the European Space Agency's Hera mission is set to visit the Didymos system in 2026 and will better see the impact crater. Andrew Rifkin then returned to the podium and showed images of Didymos' discovery in 1996 and more recently from the Lowell Discovery Telescope. He explained how scientists measure the varying brightness of the system to determine when Dimorphos passes in front of Didymos. Going through 2023, dozens of telescopes will image the Didymos system to monitor the impact and ejecta. Rifkin showed several images and image compilations of the immediate impact. Already, scientists are discussing whether the surprisingly bright impact is a result of unused propellant aboard DART or vaporized rock from the impact. Scientists have also already observed longer-term ejecta evolution that make the Didymos system look like a small comet. Rifkin said the DART team is now preparing to announce initial measurements regarding the impact's effects on Didymos' orbital speed. The speakers then answered questions from the in-person and online viewing audiences. One member asked about the change in speed necessary to spare Earth from a potentially catastrophic asteroid impact. Rifkin said that because the Earth moves 1 Earth diameter every 7 minutes, the beta necessary to save Earth depends on how far in advance an impact craft can strike the asteroid. Another in-person member asked about the greatest lesson of the DART mission. Cheng said the mission proves a kinetic impact is possible, and he hopes beta measurements will prove kinetic impacts can be an effective means of planetary defense. After the question and answer period, President Milstein thanked the speakers, made the usual housekeeping announcements, and invited guests to join the society. President Milstein then adjourned the meeting. The temperature in Washington, D.C. was 20.5 degrees Celsius. The weather was cloudy. Attending in person, 42 people, concurrent live stream viewers, 67, for a total live viewership of 109, and the number of online reviewers in the first 2 weeks of posting, 344. Respectfully submitted on behalf of Recording Secretary James Heelan.
Well, thank you very much, Janice, for reading the minutes. We now turn to tonight's speaker, Mark Clampin, and his lecture on NASA's Astrophysics Exploration Program. Mark is Astrophysics Division Director in the Science and Mission Directorate at NASA headquarters right here in Washington, D.C. He's also co-investigator on the Transiting Exoplanet Survey satellite, known as TESS, and on the Advanced Camera for Surveys science team. Before moving to headquarters, Mark was the Director of the Sciences and Exploration Directorate at the NASA Goddard Space Flight Center. And while at Goddard, he served as observatory project scientist on the James Webb Telescope. Before joining Goddard, he was with the Space Telescope Science Institute, where he served as group lead for the Hubble Advanced Camera for Surveys and worked on the first 4 Hubble servicing missions. Mark's research interests are focused on studying the formation and evolution of planetary systems. In addition to his work on space-based systems like Hubble and JWST, Mark has also designed ground-based telescope instruments, including adaptive optics systems, coronagraphs, and detectors. In addition to other honors and awards, Mark has been awarded a meritorious Presidential Rank Award and NASA's Exceptional Achievement and Scientific Achievement Medals. He is a fellow of SPE and of the Royal Astronomical Society, and he served for many years as chief editor of the SPIE Journal of Astronomical Telescopes, Instruments, and Systems. Mark earned a BS in physics at the University of London and a PhD in astronomy at the University of St. Andrews in Scotland. All questions will be held for the Q&A after the lecture. And Mark, the stage is yours.
Okay, good evening, everybody. So, as Larry said, I'm going to be talking to you about NASA's astrophysics program. Let me just get my hands right here. So I'm going to try to sort of walk through the space missions that we build and fly and try to enlighten people on the science goals that we're trying to achieve with these missions. So let me start off with a really high-level statement about what we're trying to do in astrophysics. And basically, very simple goals here. We're trying to discover how the universe works, explore how it began and evolved, and we're also trying to search for life on planets around other stars. And as Larry said, that's an area that I've done most of my sort of research in over the years. So that really breaks down into 3 broad scientific questions. And the first one is, how does the universe work? And what we try to do there is probe the origin, the destiny of our universe, and understand the nature of black holes, and then mysterious things like dark energy, dark matter, and gravity. And I put a few examples of some of the things that we've done in the past to try to address those goals. So on the left here, you see a very detailed map of the cosmic microwave background, the sort of signature of the Big Bang. And this was taken by a satellite called WMAP. We also do a lot of support of basic research and analysis programs, such as astrophysics theory. And in the middle here, you can see an image of a black hole simulation. And this is using relativistic astrophysics and supercomputers to try and visualize what a black hole would actually look like and how the gravity affects, you know, the physics of the optics as we look at these things. And then finally, on the right, this is just a very simple diagram just explaining that, you know, visible matter in the universe constitutes about 5%, and 68% is dark energy and 27% is dark matter. So it basically says we're seeing a very small part of the universe when we study it, and we really, as astrophysicists, don't understand dark energy and dark matter that well yet, which is one of the reasons we conduct these investigations. So the next question, as I said, is try to answer the question, how did we get here? And this is really exploring the origin, the evolution of galaxies, stars, and planets that make up our universe. And the way we do that is by taking very deep images of the universe, in particular with Hubble, and then try to understand how stars and galaxies have evolved over the history of the universe. And I'll come back to the Hubble Ultra Deep Field shortly. And then on the right here, we also study regions where we know stars are being formed. And what we're trying to do there is understand how stars are formed, what are the physical conditions to create stars, and then as they form and evolve, you know, what are the conditions that lead to planetary systems around those stars? You know, does every star have a planetary system, or is it a sort of random process that comes down to where the star is in the cloud and what's surrounding it, you know, such as, you know, very hot stars? And then the final broad question is, are we alone? The search for life, and this is the one that everybody's really excited about. And I was asked the question just as I came up here. And what we're trying to do here is really discover and study planets around other stars. And for the last 15 to 20 years, we've really undergone this amazing transformation in our understanding of this field. So when I started at Space Telescope in 1986, colleague of mine, Robert Brown, had just written a paper speculating that you might just be able to image a planet with the Hubble Space Telescope. But the consensus of his colleagues was that it probably wouldn't happen. In reality, we did not actually get to image the kind of planets he was talking about with Hubble, but we've been able to do a lot of other things as this field has developed over the last 20 years. And I'm going to talk a bit about the key technique that kind of made all that happen. But before we looked for planets, what we looked for was the signature that planets might be there, and that's looking for the dirt and debris that's created when planetary systems form. And if you look at our planetary system from a very long distance away, you'd see a lot of scattered light from both the asteroid belt and also from the Kuiper belt, which is outside the orbit of Neptune. And that's basically the debris and material left over from the formation of our solar system as it's evolved over the years to, you know, the planets that we see today. But that material contains a lot of dust, and if you've ever dropped a bag of flour in a sunny kitchen, you'll know that you can see that you know, flour scattering lots of light, and it's the dust that scatters light. So before we could image planets, or you know, at least study them, if you wanted to find planets or the possibility of planets might be there, you went and looked for dust disks like this one around a star called HD 107146. And this is actually what we did with an instrument I built back in the late 90s called Advanced Camera for Surveys. More recently, with telescopes like the Spitzer Space Telescope, which works in the infrared, we've actually been able to map weather on some of these planets as we've got more and more skilled at studying these planets without actually taking images of them. And just here, this is the current count as of this afternoon. So right now, we know that there are 5,187 confirmed planets around other stars. And the really cool thing is that many of these are small rocky planets that are potentially in habitable zones around their stars, and that's the zone where you could have liquid water. So let me move on now. I think this captures, what we're doing and why we're making the observations that we do. But the way we really structure the astrophysics program is around the National Academy decadal surveys. And every decade, the National Academy conducts a survey and makes recommendations on the priorities for science observations in astrophysics. They also do this for other fields like science, planetary science, and heliophysics, and basic physics as well. But the Astrophysics Decadal Survey, they generally recommend a balanced portfolio of small to large missions, and each decade they recommend one mission that we call a flagship, or a large observatory. And in 1972, it was the Hubble Space Telescope here. The following decade, they recommended Chandra, and in 2000, they recommended the Webb Space Telescope. So I'm going to start by just talking about those for a few minutes. So I think everybody's heard of the Hubble Space Telescope by now. It's in its 32nd year of operation, and it's really rewritten the textbooks in every area of astrophysics that we can think of, all the way from taking these extremely deep images of the universe. So these are some of the deepest visible to near-infrared images that have been taken. This one's I think the Hubble Extreme Deep Field. They kind of ran out of things to call it. They started off as a deep field, and then they were the ultra deep field, and then it was the extreme deep field, and so on. So this one, I think, is the last one that was taken, which is the extreme deep field. And it's looking at galaxies all the way back to about 1 billion years after the Big Bang. So these are the smallest, reddest objects in this image were galaxies that formed about 1 billion years after the Big Bang. And one of the really interesting things that Hubble did was make us ask the question, when did the very first stars and galaxies form in the universe, and how would we observe them? So I'll come back to that in a minute. But one of the interesting things about Hubble is that in addition to answering the science questions that we wrote down when we started this program back in 1972, when they wrote the decadal survey recommending this mission, which was to understand the value of the Hubble constant, it has done so much more, including many things that we never even imagined back in 1972. It's gotten spectra of Jovian planets around other stars. It's been able to take pictures of the optical counterparts of big bursts of gamma radiation in the universe, and it's helped us discover dark energy, which I'll come back and talk about in a while. So Hubble has really changed how we see the universe and how we think about it. And then the following decade, the recommendation was for a large X-ray telescope, and that's the Chandra Space Telescope. And in fact, the director of the Space Telescope Science Institute, Ricardo Giacconi, was actually a major factor in getting this telescope recommended and then into the design. And Chandra has also really opened our eyes to many different areas of astrophysics. So it's been able to help us study protoplanetary disks in clusters. It's been able to help us map out dark matter that we can't see through X-ray radiation. And it's told us a lot about black holes, jets, and how galaxies grow. So it's really contributed a lot of new science as well as Hubble. And one of the really sort of iconic images is the one on the left, which is a composite image taken in different emission species of atoms like carbon, oxygen, and calcium. And this is actually a supernova remnant. So it's actually the remnants of a large supernova explosion that created all these heavy metals. And just a reminder for astronomers, anything heavier than helium is a metal. So it's really done a lot. And this was, again, a great recommendation by the National Academy. So then that brings us to the 2000 National Academy recommendation, which was to build a large infrared space telescope, which was named by previous administrator, the James Webb Space Telescope, after the second NASA administrator. And this telescope's very different from your sort of traditional mom and pop, mirror in a tube kind of telescope. It's designed to work in the infrared, but it's an infrared telescope that we want to have for a long time. It's meant to be an observatory facility. So that means that the traditional way that we've always called infrared telescopes, which is with a large dewar of liquid helium, isn't the way we wanted to go with this telescope, because the helium would have boiled off after a couple of years, and then we'd have been left with a warm infrared telescope. So what we did is we designed a telescope that had this array of membranes, and they're about the size of a tennis court. And we fly the telescope so the sun is always on the other side of the telescope, and that allows the optics of the telescope and the instruments to stay in the shade. So you saw the video there, which was a really key moment. This last year, the telescope launched on Christmas morning, and I, for one, was absolutely astonished at the number of people who stopped me in the street when I took the dog for a walk that day on Christmas morning to congratulate us on this successful launch. And this telescope has just kept making firsts. So it took us 2 months to deploy this telescope. One of the problems I should have mentioned with the structure here is that it doesn't fit in a telescope fairing. Sorry, it doesn't fit in a rocket fairing. So you have to fold up the telescope and those big membranes and then unfold them once you're in space. So that took us 2 months, and we were all biting our nails while that was happening. We tested it again and again on the ground, including the software. Somebody was asking me about software earlier. Everything was tested many times over to make sure that it would function as we designed it to, but it was still a big relief when it did. So in July, we had the very first release of data from the James Webb Space Telescope, and this is one of the first images. It's a deep image, very similar in the way it was done to the Hubble deep fields, except this image is infrared. So it pretty much begins where Hubble leaves off and goes all the way out to 5 microns. So it's built from 6 different images taken at 6 different infrared wavelengths between 1 and 5 microns. And just remember, your eye kind of cuts off at 0.7 microns in the red. So what are we looking at here? Well, we're looking at a field of galaxies. And in fact, this is just a reminder about how smart Einstein was. So this is what we call a supercluster. So all of the galaxies you see in this field that are white or yellowish are part of a supercluster of galaxies. And they are actually bending the light and re-imaging galaxies behind them. So all of the smeared galaxies that you see, like this one here, all these arcs or wisps, are images of galaxies that are way behind this supercluster. So that's a pretty amazing thing, and depending on where they are in this image, those galaxies can be magnified by up to 100 times by the gravitational bending of the light. So in addition to the performance of the James Webb Space Telescope getting us much deeper than we've ever been able to see before, we're also getting an extra sort of kick from Albert Einstein as well. And this image is really hard to appreciate when you see it like this. So I kind of zoomed in on a bit. And these are stars, and it's a hexagonal telescope, so you get a funny-looking pattern, not the traditional sort of cross that you see in bright stars. But you can see all these faint galaxies here, the wisps from the lensing. And we're seeing some really interesting stuff. So this has just been published by a couple of different authors. They call it the sparkler. So you can see this is a sort of strip of galaxy, and it's surrounded by all these little bright dots. And what you're looking at there is a galaxy that is way behind the supercluster, and there are blocks of stars that we call globular clusters. They're very old stars, and they've all been kind of magnified as well. So we're able to see these extremely old stars that probably formed very early in the universe. The claim in the paper I've seen is something like 500 million years after the Big Bang. And we actually can image individual globular clusters with this telescope, which is just simply amazing. So this telescope is going to just keep on giving and giving. This image was taken in 12 hours, and it's already deeper than the deepest Hubble deep field in terms of its sensitivity. So when we start doing, and we have actually begun them, the very deep imaging programs where we spend hundreds of hours taking very deep images, we're going to really be able to push back to that time around 1 to 300 million years after the Big Bang, when we think the first stars and galaxies formed. So this is just a truly amazing image. And I should just say, actually, I should have mentioned that this particular galaxy, the sparkler here, or wisp of galaxy, I should say, actually appears about 3 or 4 times in this image. It's multiply imaged, and you can find it in different places around this image. So as something to do over coffee on Sunday morning, I guess. And this is another one I wanted to show. This was released this week. I think a lot of people have seen this iconic image of what are called the Pillars of Creation, or the Eagle Nebula. It was a very popular Hubble image back in the middle 90s. It was when it was first taken with the Hubble Space Telescope. So this is the Hubble image on the left here. And on the right, you see the new James Webb Space Telescope image. And the difference is that the image on the left is taken in visible light, light your eyes could see. And the image on the right is taken in infrared colors. And so you see immediately that there are all these stars, because we're seeing through a lot of the dust and into the nebula where stars are being born and formed. And the really neat thing about this image is you can just keep zooming in. And as you zoom in, you can start to see disks around some of these stars, and really study how stars are being formed and then how they evolve in these big dusty clouds. So this is just an amazing example of what the James Webb Space Telescope can do. And these images are online. You can go to the Space Telescope Science Institute webpage, download them, and see them for yourself. So I'm going to finish up by just talking a little bit more about one last Webb result, and that's studying exoplanets. So back around early 2000, when we started discovering exoplanets using a technique called radial velocity, or wobble, from the ground, people suddenly realized, well, if we're seeing these planets and they only have periods of a few days, they're probably going in front of the star that hosts them every few days, and some fraction of those will actually cause the light from the star to dip a little. And in fact, that's what happens. It's called a transit. And as the planet moves across the face of the star, like it is here, you see a dip. And then when the star gets to the other side, you're back to the standard level of starlight. So you can actually detect planets, very big ones, with a celestron. And the very first demonstration of this technique was done in a car park in Boulder. And it used a celestron telescope with a CCD detector of the kind that you now find in iPhones, or whatever your favorite kind of mobile phone is. But this is a technique that is really powerful, and I kind of think of it as the gift that keeps on giving. Because if you think about what a planet looks like, and if you've ever seen an image of the Earth from the space station, you'll see that thin annulus of atmosphere as the stations are moving across the Earth. And it turns out that you can actually get information about the atmosphere of the planet, because starlight is coming through that thin gray annulus, which is the atmosphere, and you can make these transit observations at different wavelengths and then separate out the contribution from the planet's atmosphere. Now, this technique was first done on very large, puffy Jupiter-like stars with Hubble in the visible, and This was one of the first things we did with Webb for this early press release in January. And this is an example showing a spectrum where we disperse the light from 0.75 to 2.75 microns. This is a gas giant planet. It's called WASP 39b. WASP is the name of the survey that found it. And you can actually see the white points of the data, and they actually track these big water features here. So what this is telling us is this planet's very hot. There's a lot of water on it, but it's all in the form of steam. So for people like me who work in this field, this was a real epiphany, seeing this kind of data quality from one observation. And I'll talk a bit more later about what we can do with that. So after the James Webb, the 2010 decadal survey recommended a very different approach to the next large observatory facility. That facility is now being called the Roman Space Telescope, and it's a 2.5-meter telescope. So it's actually the same size as Hubble, but it has extremely powerful infrared detectors of the kind that we built for the James Webb Space Telescope, and it has a lot of them. So this just gives you a sort of layout of the focal plane. So each of these is a detector, and it basically provides something like 100 times the coverage of a Hubble Space Telescope image. So that's a very large part of the sky you can see at any one time. And this telescope is designed to do big infrared surveys. And that means it produces a lot of data, and that data needs to be reduced and analyzed very quickly to get the maximum value from it. And what are we trying to do with this? Well, what we're trying to do is study dark energy and try and understand why the universe is starting to accelerate as it expands. We're also trying to understand the nature of dark matter, and then we want to do lots and lots of different infrared surveys with this data. And we're also trying to finish up with an exoplanet census. And this is trying to understand what we still don't know about exoplanets, which is most of the ones that we look at the moment are a very biased sample selection. And what that means is we've only been looking at them for 15 years. So what we're trying to say is, how many planets are there out there that have periods much longer than 15 years? And there are different ways you can study exoplanets, and I'll show you one now. So I fear this graphic on the left is going to be too hard to see, but it's basically illustrating that the universe is, based on the observations that we've made, is starting to accelerate as it expands. And you can see it kind of turn over and start speeding up right here. Let's see if we can get that just there. So this was, a key result from the Hubble Space Telescope, but we still don't know what dark energy is. So we're going to use the Roman Space Telescope to study that. And these terms here sound very fancy, baryonic oscillations. What it means is we're just studying the distribution of galaxies as a function of age of the universe. And then in the second one, we're studying supernovas. And certain kinds of supernovas are what are called standard candles, which means that we always know how bright they are. So if we look at two and one is brighter than the other, we can deduce distances. So we're also measuring, using these supernova as distance measurements, a very high precision out to much larger redshifts than we've been able to do so far. And that will allow us to really understand and try to nail down what is causing the expansion of the universe to accelerate. And then we're also doing one other thing, which is we're trying to study the nature of dark matter. And the way we're doing that is by taking images of millions of galaxies and then studying how their shape is slightly distorted by dark matter in the universe. And that will allow us to sort of reach a statistical conclusion about the nature of dark matter. And then the other thing that we'll be doing, which is something I just mentioned, is looking for exoplanets. And this comes back to Albert Einstein and gravitational lensing. So occasionally, a foreground star will pass in front of a background star, and you'll see a very small enhancement of the signal. And if there are planets, you actually see a blip in the signal as the star image in the background is enhanced. And you can see just here, again, it's hard to see, but we see these very small blips. So by taking an image or a survey of images of the center of the galaxy and just repeatedly taking images, we will be able to find these what are called microlensed planets, and that will allow us to map out the outer regions of solar systems around other stars and fill in that missing piece of information. But it will also allow us to do other things. And just in the last couple of months, there have been a number of papers that were published where people think they found what are called naked or isolated black holes. And these were found just by virtue of the fact that they magnify whatever's behind them as they move with respect to the telescope. So we're actually seeing in a couple of surveys the very first evidence of these isolated black holes. So we will be able to study the statistics and therefore understand the nature of these objects using the Roman Space Telescope in its very deep surveys. And then, as I said, there's all these other things you can do with the survey. You can measure astrometries, you can get very precise precision measurements of the locations of stars. You can understand the nature of these regions where stars are born. You can study how stars pulsate, and we need to understand that to really understand the nature of planets around these stars. You can take direct images of exoplanets. You can study planetary system diversity. There's just an incredible number of different astrophysics programs you can do with these kind of very deep, very powerful surveys. So I should just say this telescope is scheduled to launch in 2027. And we're making a lot of really good progress putting it together. So the other thing I wanted to talk about is time domain and multi-messenger astronomy, and then we'll talk a bit more about exoplanets. So this is kind of a new area of astronomy. It's not new, but it's become very important with the Decadal Survey recommendation for 2021. This has been identified as a really important area that we need to focus a lot of our energy and our missions on. And it's kind of studying transient events that occur in the universe. And the multi-messenger part is studying them using different kinds of measurements or messengers. So traditionally, astronomers use the electromagnetic spectrum. But in recent years, we've been able to start studying objects that produce gravitational waves. And the National Space Foundation LIGO Observatory has been finding gravitational waves, and NASA has started to do programs to find the counterparts of these gravitational waves. And then we're also studying high-energy particles that are produced from these very transient high-energy events. Excuse me. And we're also building new missions that actually study cosmic rays, which give us a lot of information about heavy elements, again, in the universe. So gravitational wave astronomy is a very recent arrival. LIGO has only in 2015 made its first discovery of gravitational waves. And this is a technique that allows us to discover a lot of different things, ranging from looking at the very early universe to understanding pulsars, to studying what happens when stellar mass objects, such as black holes or neutron stars, collide, and other kinds of transient events that produce gravitational waves or pulsars and supernovas. So it's a lot of things that produce gravitational waves. And this one is one of the first examples of a real breakthrough using this so-called multi-messenger approach. So this is an event that was discovered in 2017. It's got the usual horrendous phone number for a name, GW170817. And it kind of got everybody's attention. It was detected on one of two gravitational wave detectors. I think it was the Hanford one that measured this. And a few seconds later, in fact, less than a second later, it was detected by NASA's Fermi satellite as a gamma ray burst. And you can see, the arrival of the gravitational wave detection, and then in 1.7 seconds later, we see the gamma ray burst. And it was also detected by the European Integral Satellite, which also measures gravitational waves. And this kind of led to one of the very first, what are now called counterpart campaigns. And what you're seeing in the video is a simulation of what we think happened, which is that two neutron stars merged. They produced these ripples in space-time that we call gravitational waves. And then you get this kilonova that produces this massive outburst of X-rays and gamma rays. And then the thing just basically produces optical light that we can detect. So this object was first caught by NASA's Swift satellite here. This is it just here. You can see that little dot there in soft X-rays. It was detected by the Chandra Space Telescope. And then after an extensive ground-based campaign, we were able to detect it with Hubble in this galaxy. And a lot of ground-based telescopes, slowly work through the possibilities based on where we think this occurred. And we eventually were able to find this object and then track it down and take spectra as the light slowly faded. So this object has really produced a sea change in our understanding of how heavy elements are produced in the universe. And if you have a gold ring on, these are the kind of heavy elements that were produced in this neutron star merger. So it's not just supernovae that produces heavy elements. We also understand now these events like merging neutron stars also produces them. And we were able to make measurements with the Hubble Space Telescope using spectrograph to show these elements and their abundance as this thing slowly faded. And there's always something going on in astrophysics. So this occurred in just the last couple of weeks. It occurred, I think, on, let me check, 10/9, so it was the 9th of October. This is one of the brightest gamma ray bursts ever seen. And it's particularly notable because it's taken a very long time to fade. This is a picture taken by NASA's Swift satellite, credited to A. Beardmore here at the University of Leicester. And what we think we're seeing here is very dramatic language here, but basically a new black hole being formed as a massive star has collapsed under its own weight and produces massive burst of X-rays and gamma rays. And the reason you're seeing these rings here is that this is an X-ray image, and what you're seeing is X-rays scattered off dust in the intergalactic medium between this object and what we see today. So this field is starting to become very interesting, and we're learning a lot more about extreme physics as we do more and more observations. And I said earlier that a key part of this is doing the theory, and this is another example of very complex relativistic astrophysics, predicting what happens if you have a merger of two black holes. And it represents, face-on view of these two black holes. One is done as orange and one as blue, so you can see where the light is coming from. And then we rotate it so that you're looking at a different angle. And you can see that the gravity of the black hole actually bends the light. So you can see behind these things. And then as they orbit each other, you can see how the gravity of both black holes interacts and produces this very strange looking effect. So this is, modeling that helps us understand what we're seeing as we start to do more and more observations of these multi-messenger objects and understand what happens when you get these interactions. So let me move on because we're starting to run out of time. So I want to just finish up by talking about the search for life and then where that takes us next. So as I said before, the number of exoplanets known now is about 5,000. These are confirmed. We know they really exist. There's another 9,000 or so exoplanets that we haven't confirmed yet that are just considered candidates. And those 5,000 are in 3,882 planetary systems. And what that's saying is that many of these planets are in multiple systems, like our own solar system. And most of them have been detected by NASA's Kepler satellite, and more recently by TESS, the Transiting Exoplanet Survey satellite, which is a mission designed to provide targets for the James Webb Space Telescope to study. And you can see here in this graph, this is just the number of detections by discovery year. So you can see where TESS and Kepler kind of kicked in and started producing lots and lots of these observations. So the number of planets we're discovering is just going up very, very quickly. And TESS is making lots of new discoveries now in its extended mission phase. And many of these planets are potentially habitable. So this here just gives you a sort of sampling of the kind of things that we're finding, and they're shown in scale compared to Earth, Mars, Neptune, and Jupiter. And many of these, are pretty close. Proxima Centauri is 4 light years away. Ross 128 is 11. And you can see, we are seeing them all the way out to 1,000 light years, depending on which survey found them. And the ones that are really interesting are systems like the TRAPPIST. And this is not named after the beer. It's named after the name of the survey that found them. And the TRAPPIST system looks like the one at the top. So you see it's got 7 planets, and that green region indicates what we call the habitable zone, where liquid water could exist on these planets. The interesting thing is that it's a very different system from our own. So TRAPPIST-1 is what we call a red dwarf. It's a very low mass, very cool star, which is why it's called red. And so those planets actually are very close in to the star. And you can't quite see the lines here, but they basically are shown here. This is the TRAPPIST system just there compared to our own solar system. So they have periods of days, and most of these planets are also tidally locked, like our moon. So they're interesting, and we will search them and study their atmospheres with the James Webb Space Telescope. But they're very extreme compared to our own solar system. So we don't know what we'll find. And I mentioned how the transits work. So you can see when you have a system like this, where you've got 7 planets that all have periods of days, you can just study these with JWST and keep coming back and coming back and coming back. You don't have to wait for a year for the next transit like you would with our own planet. And this is just another example of the kind of data that James Webb is taking. This is another Jovian gas giant planet that was taken very early on in the program. This one is called WASP-39, and you can see that with this one we've been able to detect carbon dioxide for the first time at 4.5 microns. So this is a brand new result, and it's the first time we've ever detected this feature spectroscopically. So it just shows the power of this telescope, and as we start to study these smaller rocky planets and try to probe their atmospheres, we're going to make some interesting discoveries, I think. And then finally, I just want to finish up by saying that, the holy grail for exoplanet science is actually being able to take an image. And remember, with the transit technique, you never actually see the planet. You just see the effect of the planet because you're looking at that dip in the light and the absorption that's created by the atmosphere. So we want to take images of real sun-like systems with Earth-like planets. And that's the next thing that we're going to be trying to do. This is an example of a system that was taken by the Hubble Space Telescope. You can see this beautiful dust ring here, very similar to the Kuiper Belt in our own system. And we thought we'd found a planet in this system, that little dot at the middle of the box that we called Formal Hut B. And we tracked it for several years, and then it kind of became very controversial as to whether or not it was real or we were just looking at a puff of dust from two asteroids colliding. So this is going to be a great target for the James Webb Space Telescope, where we will be able to see, is this a puff of dust? Did we see an asteroid collision? Or is there really a very young planet there? And these planets are going to be the order of, tens of millions of years old, which means they're still warm from their formation, so they're emitting lots of infrared radiation. So, just to sort of wrap this up, I talked about NASA's large missions, but it also operates missions at different levels. As I said, we want a balanced portfolio of missions, and the smaller missions we use to attack individual specific problems. So we have a number of missions in development that cover the whole range from sub-millimeter wavelengths all the way to gravitational waves. On the left, you see a mission called GUSTO, which will be doing imaging in the radio or sub-millimeter, and that's a balloon-borne mission. So we actually fly these on balloons out of the Antarctic. And on the right, we're collaborating with the European Space Agency to build a system called LISA, which is a way of measuring gravitational waves directly. And then in the middle, we have all these other missions that we work on that are designed to do specific science problems. And then we also have a lot of small and suborbital missions that fly on balloons or fly on what are called CubeSats. Some of these are to test technology. Some of them are basically to train the next generation of US principal investigators for larger missions. And some of them are just to address a very specific science problem that you might be able to do with a small CubeSat-sized mission. And the mid-X is kind of the in-between. These are what we call mid-class and small explorer missions. And in general, we pick mid-X's to address a particular scientific problem that may not have been addressed before. So TESS was the first time that we had looked for very bright stars with transiting exoplanets because we wanted targets that the James Webb could follow up. NISA is designed to look at very transient X-ray signals from pulsars. So we pick these missions to address specific problems. And then the small explorers are extremely focused science investigations. And as I said, GUSTO is a balloon mission. IXPE at the top is designed to look at polarization of X-rays in supernova remnants. So a very balanced portfolio allows you to do a lot of research analysis, develop technology, and also address a wide range of different scientific problems. And just to give you an example, NuSTAR was a great explorer mission that was able to study X-rays. And when I say close to home, I mean X-rays from solar flares. It also allowed us to look for black holes in very dark, dusty and gas-rich areas. And we were also able to study, undead stars or neutron stars using this technique. And it's been used to study supernova as well. The other one I mentioned was the NISA, the Neutron Star Composition Explorer. This one sits on the International Space Station, and basically it measures transient X-ray signals. And using those, we're able to study questions like, what is the mass of a neutron star? And we're also able to see things going on the surface of the neutron star based on how the X-ray signal is modified by these sort of dark spots on neutron stars and magnetars. So this is the NASA fleet as it currently stands. And as I said, we have this range of missions to attack different problems. And as I said at the beginning, the guidance on how we do this, comes from the decadal surveys each decade, guiding us to a specific problem for the large observatory science, and then recommending RNA programs and technology development, and then specific problems that we should attack with the mid-class and small explorer missions. And then also, what they call state of the profession, or development of future scientists using the very small missions, which can address very pointed science observations, but also train the next generation of scientists to build flight hardware. So I wanted to finish up by just addressing where we go next. And this is really the sort of last word from the 2021 decadal survey. And you can see here, we've had waves of great observatories. So the first wave was Hubble, Compton, Chandra, and Spitzer. The second wave has been Webb and Roman, and NASA is now ready to pivot to the third wave, and this is the primary recommendation of the 2021 decadal survey. And basically, what they're recommending is a program of future great observatories. And the first one is best summarized like this. So they want us to spend the next 5 years developing technologies to initiate the formulation of a mission that will have something like a 6-meter aperture that will be able to directly image Earth-like planets around Earth-like stars, and then collect spectra so that we can look for biosignatures and determine whether those planets might be habitable. So that sounds, based on what you've seen so far, I hope, like it's not that hard, but it's actually extremely hard. Because if you're going to take an image of an Earth-like an Earth-like planet around a Sun-like star, you need to get contrast levels of 10 billion. And the best we've been able to do so far, which will be the Roman Space Telescope, we're shooting for something like 10 to the minus 8 or 10 to the minus 9, and we need to go another 1 or 2 orders of magnitude to get to 10 billion. And these planets are extremely close to their parent stars, so you have to find a way of basically suppressing a lot of light in a very small area. And just to sort of give you some idea of what that means, when you're driving home tonight and somebody's coming the other way with their lights on beam, you kind of go like this. And that's basically what coronagraphs do, except you're probably trying to block out light that's maybe 1, 2 orders of magnitude brighter than the area around it, whereas we're trying to block out something at 10 billion times. So it's an extremely complex problem. And what it really means is, if you think about the James Webb Space Telescope, we built all the optics on that telescope to nanometer precision. And this next telescope can be built to nanometer precision. But in order to make it work and achieve the contrast, we have to go to picometer level stabilities, which is a whole new regime that we've never built space hardware in before. So this is the real challenge. It's all about metrology and understanding how your system's moving at a level that we 5 years ago couldn't even contemplate measuring. And what we're trying to do, as I said, is get images of these Earth-like planets and then collect spectra so that we can understand about the nature of the planet and whether it might be habitable. And what that means is we can't just think about our Earth as it is today. We have to think about what it might have looked like as it was going through its evolution over the last, many giga years. So, modern Earth spectrum looks like this. But if you go back, to the Proto-Erozoic Earth, it looks very similar, but not quite. And then when you get to Archean Earth, it looks very, very different. So getting spectra and being able to sort of understand these different compositions in the atmospheres is going to be critical to understanding the habitability of these planets. And finally, just to finish up, I can see Larry there ready to come up. This is just a couple of the concepts for what this telescope might look like. So one concept that was proposed to the National Academy was a 6 to 8 meter telescope called LUVOIR-B. So you can see the mirror just there, and there's the secondary. And it's what we call an off-axis telescope. So the light actually goes off to the sides for the secondary mirror, which means we're not blocking the view of the primary mirror with any apertures that might cause diffraction. And the kind of image we're looking for is the one you see at the top. This is what our own solar system would look like, taken from another star. The other technique that's been proposed is called HabEx. And instead of having a system on board to block out that bright light or star, it actually uses a separate free-flying occulter like this. So it's kind of a big, dark structure with these very fine petals, and that allows you to block out the light. And then you have the telescope down here, a couple of 100,000 kilometers away. So you have to fly these two in very close alignment so that you are blocking out the light from the star that you're trying to study. And then if you're lucky, you'll get an image that looks like this, dust ring, like the formal hut one, and then the detection of these planets. So this is where we're going next, we hope, based on the recommendation of the decadal survey. And this will require lots of investments in new technology. And we have a range of aerospace companies that are really interested in working with us on this. And we're really looking forward to the challenge of developing and implementing these technologies. And I will finish there. Thank you.
Thank you, Mark. We have time for some questions. So with that, let's start with Bob Hershey and the blue microphone.
I'm Bob Hershey. I'm a member. Could you tell us a little bit more about your slide showing the two black holes, and all of a sudden they had horizontal lines going through the center from what's going on?
So we cannot image black holes with that kind of resolution yet, but it's very important to do these simulations so we understand what happens when they merge, and the physics that occurs in these multi-messengers. So basically what you're seeing is a representation of what the black hole would look like, and in that particular video, the orange and the blue are basically the accretion disks, the material that's orbiting around the black hole and slowly falling in. And the reason you kind of see it looking like it's all bent up at the back is because of the extreme gravity of the black hole. And then as they orbit each other, you get all these distortions in the light coming from the two black holes.
Okay, the distortion is the action of the two black holes on each other?
Yes, I mean, it's the interaction of the two black holes and the gravity of the two black holes, which is having a very strong effect on the, bending the light effectively.
Question from the red microphone somewhere. That would be Frederica.
Right. I am Frederica Durima, I'm a member. Thank you very much. That was a terrific excursion through a lot of things and many questions regarding the web, but my question is, that intrigued me, you talked about the TRAPPIST system, that it seemed to be that is a much more compact system and the planets rotate at higher speeds. So by the physics, their atmosphere, maybe is it anything close to the atmosphere of the Earth in any of these planets, given the speed that they're rotating and things like that?
So the answer at the moment is we don't know. But the point with that system is that the host or parent star is extremely cool, which is why they can be that close in and still have a habitable zone. We also know there are exoplanets that are orbiting extremely close to sun-like stars, much closer than Mercury. And you can Google these things, lava worlds or roasters. There's a lot of exoplanets that are totally uninhabitable because they're so close to their parent star. Right. And those stars, in some cases, are real solar-like stars. But most of these systems like TRAPPIST, where you have a very cool central star, the planets can be very close in because the star is so cool.
Right.
Yes, my name is Scott Matthews, and I'm a member. I have a question about the optics that would go on a next-generation space telescope. You mentioned something about having picometer level precision on these optics. And so, one, I'm wondering, you know, at what point are you adding and removing individual layers of atoms in order to make these optics? And a related question is, what role do you see for active or deformable optics, things that are currently being used in terrestrial telescopes? Will they play a role in future space telescopes?
So to answer the first question, I'm really talking about stability and not the actual, you know, wavefront error of the mirrors. So I would expect if as you know, for example, we used a Webb-like segmented mirror telescope, the mirrors would probably be, you know, figured to nanometer precision. And what you then need to do is actively control them to maintain picometer stability. So we've already demonstrated that we can do picometer metrology on mirrors the same size as an individual Webb segment. So it really comes down to, can you build a system that will actively control the mirrors at the level required to maintain the stability. But, you know, the actual mirror itself probably isn't much more difficult to make than, you know, the current Webb segments in terms of the, you know, surface wavefront errors. To answer your second question, we already are using deformable mirrors on space missions. So Webb has a tip-tilt mirror, which basically does all the correction for the jitter of the telescope. And that's one of the reasons why Webb's requirement for jitter was 7 milliarcseconds. And one of the reasons those images are so good is because it's currently achieving 1 milliarcsecond, which is absolutely phenomenal. And part of the reason is to find guidance sensors very good, but the other part is that it's using a tip-tilt mirror to take out residual jitter or correct for it in, you know, on a 15 hertz kind of time frame. In coronagraphs, we are already in space planning to use deformable mirrors. So the Roman coronagraph, I talked a lot about the survey, but Roman is also flying a technical demo of a coronagraph that will use 2 deformable mirrors to basically get that contrast down to the sort of 10 to the -8 level. And basically what you're doing is just correcting the wavefront error to get to the level you need to get to for that contrast.
We have a question from Carl Merrill on the web.
Hi, thanks. It looks like NASA has a full plate, but I just wondered, a number of years ago, there was a lot of excitement about changes in polarization in the background radiation that might be due to gravitational waves. And I wondered if any of these new telescopes, such as the Roman, may add to that information or settle some of the questions that were raised. And the only other thing I have is that the Europeans have the SKIA telescope studying the motions of all the stars in the galaxy, in our galaxy. And does NASA have anything comparable to that, or that might expand what the Europeans have already done?
So there were 2 questions there. The first one was about polarization of the microwave background, and the answer, I think you're referring to what was called one of the BICEP studies. So this decadal survey, the 2021 survey, they actually had a number of recommendations for the development of cosmic microwave background experiments that could build on making those measurements. So at the moment, that's kind of a big focus of the ground-based community, using telescopes and balloon-borne instruments. And sorry, yeah, there was a second part that you were asking about Gaia. So
Yes.
the US is not, we do not have in our plan or in decadal recommendations an astrometry mission like Gaia. So that's really something that the Europeans have done that complements what we're doing. And we talk regularly with the European Space Agency and our colleagues in the Canadian and Japanese space agencies as well. And that helps us kind of, stay abreast of what everybody's doing. And, we try to sort of make sure that we're not all doing the same experiment, obviously. And then on big missions like Webb, we generally have a lot of international collaboration on those.
Timothy Thomas, I am a member. I think one of the most conspicuous things about our solar system is the distribution of planets logarithmically from the sun. Further away you go, the further apart they are. This doesn't seem to be the characteristics of anything you've shown us of other planetary systems. Do you expect this rule to be true for the whole universe?
So, one of the big surprises when we started discovering exoplanets, beginning in 92, 93, was that there are these big Jovian planets very close into their host stars. And as we've discovered more over the years, we are seeing systems that are very different from ours. And one of the reasons, we're interested in doing this census of the outer regions of solar systems, which we can't see with transit experiments, is to really understand on a bigger scale the distribution of planets in solar systems, which will then allow us to sort of model these systems and understand how we got to our own solar system and how others, might evolve differently.
The distribution doesn't depend on the size of the planet. I mean, Mercury could be the size of Jupiter and still have the same distribution.
Right, but in other systems, we see a lot of evidence that planets may have moved around or migrated during the evolution of the system. So you really need to understand how the planets form in the disk, the very early stages, and then track that through study of different systems to understand the evolution. As I said, right now, we don't know what solar systems look like further out because, we've only been looking for 15 years, right? So.
Okay, this question comes from Evelyn in New Mexico. She's not a member. And she would like you to talk about the scientific goals of LUVOIR when it was deployed, and specifically how those goals have changed since or during the decadal survey.
So I should just emphasize that we are not actually as yet at the point where we're selecting a particular architecture. So LUVOIR is just one of several potential architectures. The basic science goals of LUVOIR will be to do a survey of solar-like stars to look for Earth-like planets and then determine their habitability or potential for habitability by taking spectra. It will also conduct what's called a general astrophysics study program. So that might mean very wide field imaging. It's probably going to involve doing studies in the ultraviolet. All of these things are to be decided exactly how we're going to do this and what general astrophysics capabilities we will build in as we start to formulate this mission. So right now we have two what NASA, or what we call strawman designs, and as we go further and start doing technology development, that will allow us to hone in on the architecture that we think will meet the science goals that the decadal has laid out.
Red microphone.
I'm Alan Gottfried, a member. I have two questions. The first is, we're hearing so much about black holes. What is their purpose or function? The second question is, just suppose we find that exoplanet that meets all the criteria for supporting life. What then?
So basically, the reason we study black holes is because we believe they may play a key role in the evolution of the universe, and basically may be a major player in governing how galaxies evolve as well. We believe there's a black hole at the center of our own galaxy, for example. So, they play a major role in the evolution of stars and galaxies at a lot of different scales, all the way back to early in the universe. So if we can understand them, then that helps us understand these science goals that I laid out. As far as your question, I think that's something that a future decadal survey would want to, talk to the science community. Now, the fact that we find, an exoplanet that may potentially be habitable doesn't mean it is. And, we will obviously devote time to studying the atmospheric composition, but ultimately, that's kind of what we can do now. In the future, with different technologies, we may be able to think of different experiments that we can do further on. One that has been proposed many times in the past is a very large interferometer that could image over very large baselines to get a much sharper image, but that technology right now is way away from where we are in terms of what we can do.
Let's take the blue microphone, then we'll take the red microphone.
Hi, I'm Mike Hammerschlag. I'm a journalist.
Are you a member?
No.
You're a frequent flyer.
Apparently. My understanding of gravitational waves was that it was an extraordinary coarse measurement, and in the beginning I kind of didn't understand how they could really glean any information from it, but this fascinating gravitational lensing that you see with all these stars in the deep field thing, it really is amazing. I've got to study that for about an hour watching those orbiting black holes. And apparently that's just the gravitational effect on light. How much is that magnified? It's actually, it's not just being smeared around, but it's really being amplified. What order of magnitude is that being amplified? Have you seen any evidence of exoplanets in that? Or is your resolution good enough to even, see the possibility of that now?
Typically, in those images like the JWST deep field I showed, you may be able to resolve globular clusters, but you certainly couldn't resolve individual stars, although you might see, a supernova, for instance. You certainly can't get down to doing anything with exoplanets. But, in most of these gravitational lens images, and there's a lot of them, these supercluster gravitational lenses, typically, the magnification factors can be 2 to maybe 100 in very specific parts of the image.
Good evening. Bilal Sleiman, member. First, I'd like to say thank you very much for the wonderful presentation and your service and contribution to this field. It's amazing. I have two areas I'd like your input on, if you don't mind. The first, when I see this presentation and all the data, the first thing that comes to mind is the accuracy of the numbers and the measurements. How does NASA deal with that? How do they go revise the accuracy and make sure that the readings are correct? Have they ever went back and said, oh, sorry, this is inaccurate or faulty equipment? Or how is that handled usually at NASA? Especially when, like you mentioned, it's getting finer and finer, and the plan for the future, it gets to more accurate reading. And you did give an example of a situation where thousands of miles away to work together into one system, plus the cosmic delays and everything. So there's so many factors that someone like me on Earth is wondering, how is NASA making sure those things are accurate? And then my second question would be regarding the location of things. Like you mentioned exoplanets that NASA is monitoring, almost 5,000 of them, collaborating with other international agencies. How are you placing some sort of coordinates? Because everything is moving, even in relationship to points that are available or given that don't move. Eventually, things disappear, and a planet could just dwarf into something else. And apologies for the lengthy talk. Thank you.
So let me start with the first one. So I think the answer to that is, how do we calibrate data? And you can look at the Hubble Space Telescope, and we've done the same for the Spitzer Space Telescope and Chandra. In fact, most of the programs that we do. But to give you an example with Hubble and James Webb Space Telescope, you start on the ground. So you build your instrument and you calibrate your instrument on the ground by putting known sources into the instrument, measuring how much light you see. With standard sources, you can calculate how much light is going through the instrument, what the response of your detectors are. And so before you even fly, you have a pretty good idea about how your instrument performs. The way we do it for these big observatory missions where we're really providing data to the users is once the data comes down to the ground, it goes to either the Space Telescope Science Institute or IPAC out in Pasadena, and they run the data through what's called a pipeline. So they start by taking the raw data, they populate it with all the engineering telemetry, what temperature was every optic in the instrument, all the stuff that you need to understand how the instrument was performing. And then that data goes through a set of standard calibrations that basically are designed to turn out a properly calibrated image at the other end. And we start with the ground-based calibrations. Once the instrument's in space, we start looking at what we call reference stars, stars where we know the brightness. And so we basically just take pictures of those stars and we can check the ground calibration of our instrument. And so we basically build up a calibration for the instrument or the modes of the instrument, and that then gets put into reference files that are used to calibrate as the data goes through the pipeline. And then over the life of the mission, we come back and look at those reference stars every month, every 2 weeks, whatever, and we check that nothing has changed. And most instruments over the lifetime of a mission will start to show some change in performance, because space is a pretty ugly environment. And so we make adjustments to the data analysis pipelines so that the data in the archive almost always has the most recent reference files. So you always know that your data's got a great calibration to start with. And then you have the users who need that extra bit, and they will wrap a calibration program around their observations so that they have all the data they need to make the measurement. So, and the second part was, I think it was really how do we know where to look? And basically, everything we look at is in a catalog, and we feed the coordinates of the star into the scheduling system for the telescope, and that's where it goes. For transits, there's a database that's maintained by IPAC at Caltech, and that for every star that has a known exoplanet that transits, they have what's called an ephemeris, which tells you when the planet will actually go across the face of the star, so that when you go look at that particular star with James Webb Space Telescope, you're not wasting time because you will see the transit. So, we have lots and lots of catalogs is the bottom line.
So this question comes from Carrie Lease, APL, and a member of PSW. How has COVID and other current events affected astrophysics? And what would be the very next launch to happen for the division?
So that's an interesting question. I think we're seeing the same kind of problems that everybody is hearing about on the news, supply chain issues, which are really tough when you're building an instrument with a cost cap to a schedule. So we're seeing a lot of supply chain issues and the need to be very careful about who you take bids from. We've had some examples, for instance, where when the PI wrote a proposal, a particular company said they would bid on the contract for a particular piece of the instrument, and post-COVID, you put the bid in and they're not in business anymore, or they don't have the staff to build that piece of hardware anymore. So that's been what we've seen on the sort of space hardware side, and these things all impact our schedules and our ability to get things built. I think it's not been great for the science community, and in particular my colleagues who are early career scientists and postdocs have really, had a tough time during the pandemic, not being able to really effectively network or go to meetings and meet their colleagues, start new collaborations. So I think that's been a real, tough time for them as well.
Yeah, Jim Albert, not a member. My question was sort of about water, which is critical for life. And you were talking about in the transit, you got quite a bit of information about the dust. I was just wondering how much of the dust is water, and can you tell differences between different of the exoplanets in terms of, how much water there is, that sort of thing?
Well, yes, we're certainly measuring the presence of water in the atmosphere of exoplanets. We're also measuring carbon dioxide, as you saw. So even with a few James Webb spectra, because we haven't done that many, so far, we're already showing that we can measure, composition of the atmospheres of gas giant planets very, precisely. We'll have to see how that works when we start going to smaller planets with, harder to measure atmospheres.
So I think I'll ask a last question because I don't think there are any more in the audience. I don't have any from Zoom. These are expensive. They're a very long time frame, and they're all international collaborations. So we have a decadal survey here. The Europeans have a similar decadal survey or something like it. And to what extent do you try and coordinate and match up who's doing what to get the most coverage for the scientific questions that we can try to answer?
So we do our decadal survey. The Europeans have a very similar process, and so do the Japanese, for example. I will just note, you said, that they're all international collaborations. A lot of our mid-class and smaller missions are not. We do collaborate on the big missions especially, and then some of the mid-class ones we collaborate on, but not all of them.
Not all, yeah.
But yes, we do try to talk to each other and understand, priorities so that, we're not too, layered up on one particular subject, for instance. And a good example of that is this time domain and transient theme where, we already have a sort of international group that has met once and talked about setting up a regular dialogue so that we are looking at all the priorities and different science areas that we want to address in time domain and multi-messenger, and seeing how we can work together to get a good balance, because there's a lot of different wavelengths you have to cover.
Well, I think we all very much appreciate your coming and sharing this with us. And before you go, we have a few closing announcements. The next meeting will be the 2,466th meeting. It will be on November 4th. The speaker will be Francis Hausen. Francis is the Gregory Bright and Hildale Professor of Physics at the University of Wisconsin-Madison. And he will be speaking on IceCube, the neutrino observatory operating in Antarctica. This lecture is sponsored by PSW members Brett Magaram and Eric Enig. The 2,467th meeting will be on November 18th, and the speaker will be Tony Levy. Tony is professor and chair of electrical and computer engineering, electrophysics at the University of Southern California. He will be speaking about a new technique for seeing things in 3D, no matter what they're made of, called picographic X-ray laminography, which is being applied in particular to study the internal construction of integrated circuits. So you can imagine the strategic value of this technique, since it's non-destructive. The lecture is sponsored by PSW member Adarsh Deepak. The 2,468th meeting will be on December 2nd. The speaker will be Sean Gulick. Sean is at the University of Texas, where he is research professor in the Institute for Geophysics, co-director of the Center for Planetary Systems Habitability, and associate chair of lithosphere and deep Earth studies. He'll be speaking about the latest on the great dinosaur extinction. The 2469th meeting, the last of fall 2022, will be on December 16th. The speaker will be Rachel Klima. Rachel is planetary geologist and director of the Lunar Surface Innovation Consortium at the Johns Hopkins University Applied Physics Laboratory. She will be speaking about the Lunar Surface Innovation Consortium and about going back to the moon to stay. Please check the PSW website often for update information. And before we go, let's thank the people who worked to put the show on tonight. James Hewin and Janice Soreth for the minutes. Robin Taylor, who's hiding in the back and you can never see her, but she actually makes it all happen. Video, sound, live stream, and Zoom. Robert Thompson and Lloyd Mitchell for running cameras. Erica Kane for handling the YouTube chat. Cameo Lance for managing the room. And Bill Mitchell, who hasn't done anything yet, but will eventually edit the video. Last but not least, I will accept a motion to adjourn the meeting to the social hour. And there are refreshments at the back. Second? All in favor? All opposed? The meeting is adjourned.